Okay, so we're going to go ahead and get started with 1.1 exponent laws. So the first law that we're going to look at is multiplication. So this works when the base is the same and the exponents are different. All you have to do is add the powers. For division, instead you're just going to subtract the exponents, subtract the powers. So I'm going to go ahead and show you those two examples. So with multiplication, if we have 3 to the 4th power times 3 to the 5th power, the base will stay the same, so that's 3, and we add the exponents, so that's 4 plus 5, which we all know to be 9. The only difference for division is instead we're subtracting, so if we have 4 to the 7th power divided by 4 to the 3rd power, we end up with the base staying the same, 4, and then we subtract. So 7 minus 3 is 4, so 4 to the 4th power. Not too bad. Okay, after that, what if, however, the exponent is the same and the bases are different? So instead, what we do is we keep the exponent the same and we multiply the bases. Similarly, with division, you just divide the bases. So let's go ahead and look at those examples. So let's say we have 4 to the 5th power times 5 to the 5th power. This would be the same as 20 because 4 times 5, and we keep the power the same, 5. If you want to know how this works, think about if you were to write this out, this would be 4 times 4 times 4 times 4 times 4 times 5 times 5 times 5 times 5. And since we know that multiplication, the order doesn't matter, it's commutative. So then we can say, basically we're grouping these and we have 4 times 5, which we know to be 20, and we have that 5 different times. So that's why it's the same as 20 to the 5th power. Okay, so then next we have a similar problem, except it's division. So if we have 6 to the 7th power divided by 9 to the 7th power, you just do 6 divided by 9, which can simplify to 2/3. And that is being raised to the 7th power. Pretty straightforward, nothing too complicated yet, just practicing to make sure that you have those rules memorized. It just goes much faster when you do. The next one that we have on here is when any base to the exponent 0 is always equal to 1. So what this means is if it doesn't matter if it's x to the 0 power, that would be equal to 1. But if it's 1 million to the 0 power, that is also equal to 1. Anything to the 0 power is always equal to 1. On the other side is anything to the 1st power is always itself. So if we have x to the 1st power, that's x. If we have 7 to the 1st power, that is 7. Okay, the next one we have an example of if there is a negative exponent. So if we have x to the -1, all that does is turn it into a fraction. The negative power turns it into a fraction, so it would be 1 over x. Similarly, if we have 4 to the -2nd power, that would be the same thing as 1 over 4 squared, which is the same thing as 1 over 16. Almost done with exponents. What if we have a power raised to a power, so such as x squared squared? You are going to multiply those two exponents together, so this is the same as x to the fourth. And so I'd like to show you why this works, is if you have, let's say, 2 squared squared, this rule tells us that it should be 2 to the fourth, which is 16. But if we were to break this down, since we have numbers, 2 squared is 4, and 4 squared is 16. So that's why the rule, that's just an example of the rule being applied and broken down and why the rule works. But it's a shortcut, and it works especially well when you have variables and you can't figure out what x squared is. If you have a fraction, this should be something you've seen before, I hope, but if you have a fraction, the numerator will become your power and the denominator will become your root. So if we have x to the 2/3 power, this is the same thing as the cubed root. The denominator becomes the root of x squared. Sometimes, depending on the number itself, this problem can be easier depending on the numbers you choose, whether you want the power to be on the inside or the outside. But for example, just with numbers, I guess this one doesn't really apply the same way, but this would be the same thing as the cubed root of 3 to the 5th power, which simplified is 3 cubed root of 9. But sometimes you can take the square root of something really easily and then raise it to a power, as opposed to creating a really big number inside and then trying to figure out what the square root of that is. And a lot of this is based off of the idea that you don't have a calculator. You're working on these changes in your non-calculator section. Okay, so that was our section on exponents. And then next we will talk about logs, which are the inverse. So this first formula here, converting exponents to logs and vice versa, is probably one of the ones that you will use the most throughout this unit. I think it was my freshman year of high school, my teacher called it the swoop. I don't know why, but that's what he called it. So often when I am doing problems with this, I will also audibly say swoop. But let's go ahead and look at an example with this formula. So let's say we have the problem 3 is equal to log base 5 of x. So what we're going to do for this change of base formula, the base a is going to be raised to whatever the power of whatever is by itself on the other side. And then whatever was in the parentheses will be left alone. So what this looks like now is we have the base, just like it's the base log base 5, that base becomes the base of the exponent. So then it would be 5 to the 3rd power is equal to x. So then x is equal to 125. Pretty straightforward, nothing too crazy. Something to be noted is that if you have log base e, it's usually going to be written as ln of x, which is pronounced the natural log. So ln, please don't say that. Ln degeneris is not a math term. Instead, you say the natural log of x. Log base 10, 10 is the base that we most often use because we have 10 fingers, and most of our bases in math and science are base 10. for that reason. So since we use it so often, we don't want to take the time to write it. So if there isn't a number behind log, then that is log base 10. Similarly, if you need to convert natural logs to normal logs, then you can use this formula here. You will probably not use that very often on your exam, but that one is given to you in your formula booklet. So you would just apply it very similarly to what we did with the exponent to logarithm formula. Okay, next, we're going to look at these next few rules. These work both ways as well. So if it has the same base, similar to with exponents, these are the same rules, they just look a little bit different. If it has the same base, multiplying and adding go both ways. And then if it has the same base, then division and subtraction go both ways. So if you're combining or splitting, then those two are partners. The power rule is when you have an exponent and that exponent becomes the multiple of the log, or vice versa. If you have a coefficient in the front, then it becomes the exponent. So we're going to go ahead and look at a couple of those rules in the one problem, and I'll say which rule I'm using as I use it. Hopefully I will remember. But this first problem here, I'm going to make it a little bit bigger because I have to write so small. So let's say we have log base 4 of 2 of x minus 2 log base 4 of 4 equals 1. So the first thing I notice is that 2 in front of the log base 4. And so what that tells me is I can use my power rule to rewrite this. So when I use my power rule, I have log base 4 of 2 of x minus log base 4 of 4 squared. So that 2 in front just becomes my exponent. The next thing I notice is that since I have two terms that are log base 4, I can use my quotient difference rule. So here, this will become log base 4. And since it's subtraction, that means it becomes division. So I will have 2x divided by 4 squared, which is, I'm going to go ahead and simplify that to be 16, is equal to 1. And then here, since I have log base 4, the only way to simplify that, the inverse operation, is to convert this to an exponent. So I'm going to use that first formula with exponent to logarithm. And so then my next expression would be 2x divided by 16 is equal to 4 to the first power. If you take the steps to solve now, just like a standard equation, there's nothing extra going on. So we would multiply 4 times 16 and then divide it by 2, and we end up with x is equal to 32. Hopefully that didn't move too fast for you. If so, you can always rewind, watch it again. If you have questions, of course, add them in the comments. But I'm going to go ahead and do a problem pretty similar to that one, but it doesn't have the power rule. So I will do that here. So if I have, let's say, log base 2 of 7x plus log base 2 of 2 equals 1. The first thing I see is that I have two things with the same base. And since there's an addition symbol between, I know that this becomes product. So I'm going to multiply what's on the inside. So I'll have log base 2, and then 2 times 7x is 14x is equal to 1. And then I will use that exponent to logarithm formula. And then I have 14x is equal to 2 to the first power. And then to solve, x is equal to 2 divided by 14, which is the same as 1/7. Okay. Now, there's a section within your Delta Math where these are the, I think, level 1. And then when you get to level 2, it wants you to make sure that all of your answers are valid. So if you come up with more than one answer, you have to check your answers to make sure they work. Now, we did this a little bit, some of that going back and checking our answers in calculus, but now we get to do it again here. And what we're checking for mainly is that this rule here that says you cannot take the logarithm of a negative number or 0. So if when you plug your answer back in, you have a term that says log of 0 or log of a negative number, then that answer is not valid. So I will go ahead and give you an example, maybe. Okay, so here is log base 2 of 3x squared minus 1 minus log base 2 of 4x plus 1 is equal to 1. Now, again, the first thing that I notice is that I have something with the same base, which means I can convert to division. So I would have log base 2 of 3x squared minus 1 divided by the quantity of 4x plus 1 is equal to 1. And then here I'm going to convert from log to exponent. And so that would leave me with 3x squared minus 1 divided by 4x plus 1 is equal to 2 to the first power. I'm going to go ahead and do some algebra if you want to pause and work it out yourself. But I would multiply both sides by 4x plus 1 and then simplify, bring it all back to one side. And after I do that, then I am left with the formula 3x squared minus 8x minus 3 is equal to 0. And what this allows me to do is factor it to figure out what my two possible answers for x are. Remember the big X game, I hope. But for this one, since I have a coefficient in front, I'm going to multiply. I have negative 3 times 3 gives me negative 9, negative 8. So I'm looking for a number that will multiply, two numbers that will multiply to negative 9 and add to negative 8. And that would be negative 9 and positive 1. So once I have that, I have x minus 9 and x plus 1. And remember that because we had this coefficient in front, we need to divide both by 3 and see if we can simplify. I can. This is x minus 3. And this one, normally if they were asking for the factors, I would move that 3 over and it would be 3x plus 1. But in this case, I'm going to leave it like this because it will show my 0 that much easier. So here, I know that my two zeros are when x equals 3 or when x equals negative 1/3. Now, the problem is I can't stop here because there's that extra law about logs. I have to make sure that when I plug these two values back in, neither one of these two logarithmic terms will turn into a 0 or a negative number. So let's start with plugging in 3. If I were to plug in 3, I would end up with log base 2 of 3 times 9 minus 1 minus log base 2 of 12 plus 1 equals 1. And so here I end up getting 27 minus 1, which is 26. That's a positive number, no problem. 12 plus 1 is 13, no problem. So I know that 3 works. But now I need to try negative 1/3. So if I have 3 times negative 1/3 squared minus 1, and the term 4 times negative 1/3 plus 1. This first one, I would end up with 1/3 minus 1, which is equal to negative 2/3. And right off the bat, because that's negative, I know that this term doesn't work. But just for funsies, we can look at the second one. We would have negative 4/3 plus 1/3, which is negative 1/3, which also doesn't work. So my only accurate answer is 3. Negative 1/3 would not be an appropriate one, because an appropriate answer, just because it breaks that rule about negative numbers or 0 numbers. Lastly, we have a change of base. For a change of base, really the key that you're looking for based off of this formula. So I'm going to go ahead and put the problem down, and then I'll describe what it is. So if I have log of 2 times log base 2 of 5. Really, the main thing that you are looking for is when primarily, there are other exceptions, obviously, but the main reason you will see this is when the base of 1 is the same as the interior of the log in the other one. The reason why this is the one that comes up most frequently is because when you use the change of base formula on this section, this one becomes log of 5 divided by log of 2. And the reason why this is so convenient is because since this log of 2 is here, then these 2 log of 2's can cancel. And that means that our final answer is just log of 5. And those are your notes. So make sure that if you haven't already, you comment on this YouTube video. And otherwise, your homework is there. We will work on that in class on Monday. So you don't have to start on your homework. If you want to, you're more than welcome to. But since you're taking class as homework, that means that you can focus and save your class time for homework and extra questions. So I hope this all made sense, and I will see you all on Monday.